All right, class, I'm going to put this video together because I'm not going to be here today. So you have received this in the email about 8 o'clock in the morning this morning, and we are starting chapter 4. And so just want to go through chapter 4 with you real quick here and we go from there. So you guys know this is the homework questions. We are going to skip 4.6, but let's jam with it here. So 4.1, what is this all about? We're going to continue with our whole concept of applications of derivatives. But we're primarily going to focus on graphs now. And so this will culminate in 4 more sections, which is 4.5. But right now we're just going to do the basic graphs, and we're just going to focus on something called maximum and minimum values. That's it. 4.2, we get into a guy named Roll. Rolls did not like calculus at the beginning. Eventually he learned to like it, and then eventually he actually created some cool theorems inside there too. There's also called the mean value theorem. Anyways, pretty good stuff. 4.3 is going to talk about how the shape, just knowing the derivative and the shape of the derivative and all that stuff, gives us understanding of the shape of the graph. So real quick here, first derivative is going to tell us if it's going up or down. The second derivative is going to gives us the understanding of concave up and concave down. Again, we'll learn what that is. And then we have L'Hopital. L'Hopital's rule, again, another person, mathematician, and he was thinking about, okay, what happens when things go to infinity? That's what he wants to think about there. Anyways, 4.5, we put it all together. We're going to skip 4.6, and then eventually we get to actually real tangible stuff, maximizing costs, maximizing profits, minimizing costs, or maximizing area, minimizing surface area, all this cool stuff with tangible stuff. Anyways, that's our culmination of the applications of derivatives. That's what we're going to look at. Okay, so let's jam. Let's go through it. I'm going to have you guys write down quite a bit of information here today, so we'll talk about it. So 4.1, if you want to write down maximum and minimum values, that's what we're going to take a look at in the graph itself. And what do we look at? We look at something called the extreme value theorem. An extreme just means a maximum or minimum point. It's the extreme point on a graph. All right, an extreme value theorem says this. If I have a graph which is continuous, which means I draw this without lifting my pencil or pen off the sheet of paper, and it's continuous on a closed interval. Now let's just call it A to B. So closed interval A to B. Then I know for sure that f will have will attain an absolute maximum, and also it will obtain an absolute minimum. There's going to be a maximum value, there's going to be a minimum value as long as these conditions are met. It's continuous, and it is on a closed interval. If we want to make some graphs real quick here, just sort of see it here, it'll sort of look like something like this. And can you guys see a maximum value of this graph and a minimum? Yeah, maximum is right there. Minimum is right there, and we're done. Another graph, sort of see it here. I graphed it like this. Maximum value? Yeah, it's actually the beginning of value right over here. That's why we need it to be a closed interval. So maximum, where's the minimum? The minimum is right there. And sure enough, look at that. All the time, whenever we have a closed interval, we always have a max and a min. All right, hopefully that was helpful there. Hopefully you wrote down at least the definition there and kind of thought through what we have here. All right, let's talk about something called what is non-continuous. What makes something non-continuous? Remember how I said before, continuous just means not lifting your pencil off the sheet of paper, right? That has to be there. So just real quickly here, here's 2 things that are non-continuous. If I have something that looks like this, I go from this little dot up, and then I go across here. So notice there's no way I could graph this without lifting my pencil off. I have to lift it on top, start back a little bit lower, and then go from there. This little open dot just means this dot does not belong to this graph. Okay. All right, so in this case, is this a closed interval? Yes. It is a continuous graph? No, it is not. But the question is, does it still have a maximum or minimum point? Yeah, it actually does not have a maximum, remember, because this point right here is not part of our graph. But it does have an absolute minimum right here. So yeah, you can still have them, except the extreme value theorem just guarantees that you have them, that's all. So minimum, but no max right here. And then the other ones are like this right here. You can have two dashed lines going down, and we get ourselves this. Again, that technically would not be considered a continuous graph on a closed interval. That does not work. So does it have a minimum? Yes, it does. Does it have a maximum? No, it doesn't. Okay, so now let's go on. I'm going to just graph all of this for you, copy it down as we go. We have parts 1 and parts 2. Sorry guys, there's going to be some amount of writing to do here. And then we'll get into the nitty-gritty solving equations here. So derivatives and their graphs, part 1 and part 2. So here's what we're going to talk about. We're going to talk how many ways can I get like a maximum or a minimum. Okay. And so this one right here, these are the graphs that represent the fact that the first derivative, f prime, is going to be 0. So what happens when I get a 0 for my derivative? Well, what tends to happen is, here it is. Doesn't this a slope of 0 right here? If there's a slope of 0, I have myself a maximum point for this particular graph. Boom. I could also have a 0 slope right here, and this will give me a minimum point. Okay, and the interesting thing, I could come down on my graph and then go horizontal just for a little bit and then keep on going down. So notice this one is not a max or a min, this is a plateau. Comes down, it hits 0. At some point here, we do have a 0 slope. And then it keeps on going. It plateaued. Oh, how about over here? Yeah, it plateaued here too. It was going up, and let's just say it got a 0 slope right here, and it kept on going. So just because we have a 0 slope doesn't necessarily mean that there is a minimum or a maximum. Okay, so what are these guys called? We call it critical points, critical numbers. Where the derivative equals the 0 is called a stationary point. So all the good stuff here. Okay, but let's see some other times. Let's see some other times that things kind of don't go as well. Derivatives and graphs, part 2. Let's see what happens here. Sometimes what happens is we have something called a cusp. And look at that, there's like 4 different ways here. So notice real quickly here, a cusp means this. The derivative goes up. Notice the slope here. It goes up and goes to infinity just for a split second. And then it comes back down. So this is called a cusp. You can have a cusp that goes up. You can have a cusp that goes down and around. You can also have a corner, a little V shape right here. Boom. The slope is going one direction, and then boom, switches to a different direction. It doesn't go off to infinity like a cusp does. But there's a corner. All of a sudden there's a very quick change in my slope. All right, and this one doesn't really have a special name, but here it is. What happens is it goes up, and for a split second in time, the derivative goes off to infinity, and the slope goes off to infinity, and then it pops back into a normal range. Again, you can be going up, you can be going down, but like right here, goes off to infinity and comes back around. So f of x has a critical point or a critical number. Sometimes I say critical number. But here's the difference which takes it different than part 1, is that f of x is not differentiable at this point. So we will not be able to derive, may have a derivative at this point, either a cusp, a corner, or this little slope goes off to infinity piece. All right, so let's get some definitions going with the whole critical number. And I think with that, we should kind of clear things up. So definition, here it is. A critical number or critical point of a function f is a point C in which the domain of f such that either one of two things happen. Either derivative at that point C is equal to 0, or the derivative at C does not exist. So for critical numbers or critical points, the derivative is equals to 0 or does not exist. All right, a stationary point. That's called stationary. I'll chicken scratch a little bit here. A stationary point of a function is a number C in the domain of f such that the first derivative of c is equal to 0. So this one has to have a 0 marker there. So if you kind of think about it real quickly here, this is part 1 right here, where the derivative is equal to 0. And this one right here was part 2. Actually, no, this is part 1 or part 2. So critical numbers could give you zeros or does not exist. Stationary points always have to give you 0 for the first derivative. Okay. So let's jam to some almost exercises here. Let's think about this and then we'll jump to some exercises here. So got myself this, the closed interval method. We're going to actually find our maximum and we're going to find our minimum. How we're going to do it? Here's our requirement. Our requirement is that f is a continuous function on a to b. I'll slow down, let you guys write that in. So the requirement is f is continuous. That's something we already said before. F is continuous. And it goes from a to b, including a, including b. Here's what we're going to do. We're going to find the critical numbers of f in the interval a to b, and then we're also going to find their values. All right, we're going to find the values of the endpoints. So we're going to find the critical numbers and their values, and we're also going to find out the endpoints. And all we got to do, so don't forget values and endpoints. So once we do an example, it makes sense here. So based upon all those values we have, whether it's the critical numbers or the endpoints, we're just going to pick the maximum to the largest from steps 1 and 2. And we're going to pick the minimum to be the smallest from steps 1 and 2. And that's it. Okay. All right, before we go on to this little method of trying to figure out what maximum and minimum are, let's get used to the graphing of this stuff. Let me show you just a couple of things on graphing and then we'll jam. So exercise 1. And exercise 2. Let's jam with that. So can you sketch for me? Again, we're just getting used to graphs, getting sort of an understanding of this concept. So sketch the graph of the function f that is continuous from 1 to 5. That's cool. So graph it without lifting your pencil off the ground. And it has the given qualities. I need something that has an absolute maximum at 1, minimum at 1, absolute maximum at 5, and I want the local maximum to be 2, and I want another local minimum to be at 4. So again, once we get used to this, this will be good. So here it is. I'm going to draw myself these conditions right here. So at 1, I need an absolute minimum. At 5, an absolute max. So let me go 1, 2, 3, 4, 5. So at 5, I need a maximum. So I'm going to put it a little higher. At 1, I need a minimum. That's cool. And then at 2, I need a local maximum. So I need to go up like a little hill. So there's my 2. And then at 4, I need a minimum. So right over here, I need some kind of minimum. I could put it here. It has to be lower than this guy. But it can't be lower than our starting value, or else that one will be our absolute min. So it has to be like in this range from here to here. So there it is. Notice how I'm going to if I was going to graph this here. So notice the smallest absolute minimum value is here. The highest minimum value is here, maximum value. And notice for our local max, what happened was we get this little hump. And for a local minimum, what we do is we get this little shift from going down to going up now. And there it is. That is it. Okay, let's do one more of these sketching examples here. You could have also drawn it just like this, and everything still makes sense. 1, 2, 3, 4, 5. Put the 1 there. Put the 2 there. Put the 3 there. So actually, I can put it on a line, and then 4. Will that also work? Absolutely. It can come in gently as it did before. It comes into the top, turns around at 0 or 4, 0, and goes up. I can also make it like this. Check this out. This is cool. Can I make it a cusp? Absolutely. Is that a local minimum? Yes. Is that a local maximum? Yes. Is that absolute minimum. Absolute maximum. Is this a local max? Absolutely. Is that a local minimum? Yes. Okay. I think we're ready to get started. So now let's find these. That's our job. Oh, you know, I want to do one more graph with you guys here. So I want you guys to graph x to the third. And graphing it from -1, not including -1, and then up to 2, but including. I put a little red one in here, but that should be including 2. All right, so if I go like this here, x to the third power, hopefully you guys know what that looks like still. There's my -1, +1, +2. And we're going to go 1 down from there and graph it. So the generic x to the third function goes like this right here, right? Starts out low, goes through 0, 0, goes up high. All right, so if I'm starting at -1, be about right there, and I'm going to include a open dot because that means right there the little less than symbol is an open dot. And then it goes through 0, 0, and then 1, 2, 3, 4, 5, 6, 7, 8. All right, and we're going to graph this here. So 2 to the third power, 2 times 2 times 2 is 8. I can put that in there. Closed out this time because of the equal to part right here, and graphing it. Okay, now I got some questions for you. Do we have an absolute minimum here? Absolute minimum. Answer no, because the minimum is right over here, but this is an open dot. So with the open dot, you can get super, super close to that dot. You just can't touch it. So there's no absolute minimum. Is there a local minimum anywhere? Do you see a little ridge? No. No. So we have no absolute or local minimum. How about maximums? All right, do we have a local maximum anywhere? Local max, local max? No, because this guy keeps on going to higher and higher and higher each time, right? There's no time it changes. Okay, so here it is. No local max. Do we have an absolute max? All right, do we have an absolute maximum? Yes, we do. It's right here because it's a closed dot. We can say actually 2, 8 is a absolute maximum for this graph. All right, so absolute maximum of 8 at 2. Or we could say absolute maximum of f of 2 is equal to 8. Those two mean the same thing. Okay, so now let's get into some solving of solutions here. All right, so here it is. Find the absolute maximum and the absolute minimum values of this guy. I need to know the highest it goes. And I need to know the lowest it goes. All right, I'm going to start it here. I'm going to slow down the video if I'm going too fast here. So what I'm going to do is I'm going to take a derivative. 3x squared, that's a minus 12x plus 9. And what we're going to do here with this derivative, we're going to set it equal to 0. So rewriting the derivative itself and making it set equal to 0, and we're going to solve this guy. So notice what we're doing is we're solving the derivative for 0. And I think I can take out a 3 here. 3 goes in all 3, 12, and 9. Oh, that's cool. I can factor it now some more. Two numbers multiplied by 3 at a negative 4. And that's going to factor down into, even if you use the box method, you should get an x minus 1, x minus 3. All right, so what are we doing here then? We're solving for each of those. So what do we know so far? We know that there's possibly a maximum or a minimum right there at 1 and 3. Okay, so there's the possibly maximum, minimum. And then we also have endpoints. Notice our endpoints are negative 1 and 4. So all we're going to do is we're going to plug in the low value, negative 1, plug in all the stuff we found right there, and then we're also going to plug in the highest value of x is 4, and whoever we get as the minimum, we're going to say that's the absolute minimum. Whatever we get is the maximum, we're going to say that's the maximum. Let's go for it here. So plug in back in. Now notice it's not plugging into the derivative. Plug in a negative 1 back into this equation. So pause the video if you need to here. But we can just plug in negative 1 into all those. And I didn't show the work. I'm just going to show the answer. I get negative 14. Plugging in a positive 1 into all this. It gives us a 6. Plugging in a positive 3 into all this gets us a 2. And plug in a 4, which is the endpoint. And that's it. Okay. All right. Do we have an absolute maximum? Do we have an absolute minimum? It's a closed interval? Yes. It's a closed interval. And so absolute maximum. Ooh, we actually have 2, don't we? Right here we get a 6 from a 1. We also get a 6 from a 4. So the absolute maximum of 6 at x equals 1 and at x equals 4. Jam. Okay, do we have a minimum here? Yes. And negative 14 qualifies as a minimum here. So absolute minimum of negative 14 at x equals negative 1. All right, so just to go over it here, we take a derivative set equal to 0. That gives us critical points or stationary points. We use that as well as our beginning and end points to create pretty much the highest value and the lowest value. All right, a little bit tougher on the derivative. Give you guys 30 seconds or so. Try to do this yourself. Can you take the derivative? So notice there's a power rule right here, but what I'm going to do is I'm going to actually multiply the cube root of t into both of those. Then I don't have to deal with the product rule. All right, so I'm going to do this here. I'm going to just do a little bit of work here. I'm going to multiply this into the 8. So I get an 8 cube-written. Technically, it would just be a 1/3 power. True, true. So this times this gives us a minus t to the 4/3. How? Because this is 1/3, and this guy's a 1. So it gives us 4/3. Okay, we need to take a derivative of this guy. What is the derivative? Give you guys 30 seconds. Try it yourself first. Go. All right, I'm going to take the 1/3, multiply the 8 with it here. I'm going to subtract 1/3, 1 out, minus sign. I'm going to bring the 4/3 in front, and I'm going to subtract the 4/3. And a minus 1, right? Because we subtract 1 from the exponent. Okay, our job is now a little bit more complicated. So what we want to do here is we want to set this guy equal to, actually no, we want to simplify first. Let's simplify this here. This little negative 2/3 here, we'll take it down to the bottom, minus 4 over that 3. And now what we need is we need common denominators. So I'm going to multiply both sides by the second equation by 2/3. That's interesting. A 1/3 plus 2/3 actually makes us 3/3. So in this case, 8 still stays. 3 stays here. So I'm going to go with 4t because 1/3 plus 2/3 makes 3/3. And on the bottom, we get ourselves the common denominator that we wanted. So writing this all together underneath one single common denominator is 8 minus 4t. All right, if you want to keep it like that, that's perfectly fine. Normally we like to put it to factored form, so notice you can take out a 4 out of each of these here. Left with that right there. And that's the same value that we had. Okay, so what do we have here? We just solved for the derivative. True, true. Now what we need to know is we need to know when is this derivative going to give me 0. So I'll set it equal here to 0. And the question is, how do I even do this right there? What should I do? All right. We should multiply by the derivative, by the denominator. Now the only little thing we're going to think about was since we can't multiply by 0, we're going to have to declare that t cannot be equal to 0. That allows us to multiply both sides by our denominator, and allows us also that to also be 0 completely. All right, divide by 4 if you like, and then eventually you're going to add 2 or add 3, but there it is. So what gives us a t value? T value of 2, and also don't forget the 0. Remember, this is where the derivative does not exist. This is our stationary point where the derivative is equal to 0. So let's go with it. Don't forget we begin with 0 to 8, right? So this is our beginning value. Just real quick, just to make sure that we know here. So I'm going to go like this. See all slides. It's this right here. We're plugging in the 0 into this function again, 8 into that function. I'm going to plug in a 2, and you guys verify it, but I got a 6 cube root of 2 out of it here. If I plug in an 8, I get 0. So the winner for the absolute minimum award is 2 things. T is equal to 0, T is equal to 8. All right, absolute minimum of 6 cube root of 2 at x equals 2 or t equals to 2. All right, so hopefully we're kind of getting the gist of it here. Got 2 more problems, but they're a little bit more lengthy here. Here is my function. All right, talk to me if that's the derivative, or help each other out if you guys don't think so. But remember, it's like this. It's the derivative of e to the negative x, and the derivative of negative x, which is negative 1. Derivative of e to the negative 2, it becomes e to the negative 2. And the derivative of negative 2x gives you negative 2. So there's my derivative. I have to simplify it and then set equal to 0 and solve, just like the last one here. So I'm going to get my negative values exponents to become that right there. I'll have to multiply this side by e to the x, because remember, when we multiply numbers, all we gotta do is add the exponents. So e to the x times e to the x will give you e to the 2x. All right, simplifying as much as we can. And then putting it together. There it is. All right. We found our derivative. Okay, and then don't forget our endpoints are 0 and 1. And then whatever we get here. So endpoints 0 and 1. Let's go find our critical points. Set this guy equal to 0. And go. What do we need to do? We're going to multiply both sides by e to the 2x. Now the interesting thing is we don't need to say that x cannot equal 0, because is there ever a time that e to the 2x ever goes to 0? No, remember, it's an exponential function, never touches 0. So that's cool. That just goes, cancel and be done. All right, in this case, what we want to do is we want to be able to move e to the x around. All right, and taking the ln of both functions here, the ln of e will go away, and we're left with ln of 2 is equal to x. Okay, that's the exact value. That's cool. We could have changed forms right over here, and that would have been done the same. Change forms, and you get that. Any which way, we get ln of 2 as a possible way of seeing things. Okay, I'm going to erase that for now here. So I'm going to put f of 0 because that's our endpoint. All right. F of ln of 2. And so what we're doing here is we're setting things up so that all of them, we can cross these out right here. So e to the ln gets crossed out. Now we should be just left with, oh, we can even do that 1/2. We can do that. All right, and then those go away. I'm going to 1/2 minus 1/4. My common denominator would be a 4. Let me see where we're at on this guy here. Oh yeah, 1/4. So notice this guy's going to be a 1/2 minus a 4th, which is just a 4th. Okay, so we got 0, ln of 2 done, and then we still need the other endpoint here. which is 1. Plug in a 1, and this one's going to be a little bit tougher because this one I don't know the answer to. So all doubt, plug it in, and we go to the nearest third or fourth decimal place, and so it's approximately 0.233. Okay, so where is the maximum occurs? Let's point to look through your notes here. Yeah, the absolute maximum of 1/4 at x equals ln 2, and the absolute minimum of 0 at x equals 0. All right, that should be good. And then I think this is the last one here. All right, there's this. Okay, give you guys about 30 seconds. Try this yourself. See if you guys can get the derivative. Give you guys maybe 30 seconds to start go. All right, let me start it now as well. So I'm going to go with it here. So first derivative, 1/3 in front, x squared minus 4 stays. Subtract 1 from there, gives negative 1/3, and then derivative of the inside, which is just 2x. All right. And then let's simplify this out here. So I'm going to go 4 over here because it's this 2 here and this 2 multiplied together. 2 and 2 is 4. And then the 3 is on the bottom, and then we're going to make this x squared minus 4 on the bottom with a 1/3 sticking out as the exponent. Okay. Question, did we take derivative? Have we simplified? Yes. So we're going to check -4 and +4. We're going to check those for sure. But then we're going to check any time that we might possibly have a 0 in the solution set. That means the number itself might have had 0. So we go with it here. So set equal to 0. And we are going to declare something. We can't just multiply. We got to think about, when is this ever going to give me a 0 right here? And true, that gets me a 0 when x could be a 2 or -2. So I got to keep that already in mind. Once I have that, then I can multiply both sides by this whole feast right here. And 8 is all gone. We're left with 4x equals 0, because 0 times anything is still 0. Divide by 4 gives you 0. So I got 3 numbers that rolled out of here. +2, -2, and 0. All right, for the end, we're going to plug each of them in. All right, and I did it already myself here, but if you want to try it yourself here. All right, plugging in a -4 should get you cube root of 144. So I'm taking the -4, plugging it into x, squaring it, which is 16. 16 minus 4 is 12. -2 plugs in. -2 squared is a 4. 4 minus 4 is 0. It's 0. And then this one. So these two concocted something. Oh yeah, we got to square the -4. -4 times -4 is 16. And that's about it. Okay, for this one here, 4 goes in. 4 squared would be 16. 16 minus 4 is 12, and we're good there. Same as the top one. Okay. So here it is, maximum, and I'm using now abbreviations here. So ABS means absolute. So absolute maximum of cube root of 144 at two different spots. It occurs at a -4 and +4. And absolute minimum of 0, because everything else is positive, at x equals -2 and 2. All right, so hopefully that was good enough for you guys to get started with 4.1, and I wish you well.